The control room went silent first, then erupted. The kind of stunned, involuntary sound that happens when the universe does something it should not. A pulse train marched across the monitors, crisp as a metronome and bright as a heartbeat, tied to a compact star so heavy that by ordinary reckoning it should have fallen through itself and vanished behind a horizon. Astronomers leaned in, palms flat on the consoles, watching a signal from a lighthouse built of crushed nuclei and relentless gravity. "This should be impossible," someone whispered, and no one argued. A neutron star was standing on the cliff edge of physics and refusing to take the next step. You are about to see what happens when matter is pressed until the spaces inside atoms give way, when protons and electrons are forced to marry, and the world becomes a city of neutrons packed tighter than any earthly imagination allows. You have felt the pressure of a storm at sea. Now, imagine the pressure of a mountain balanced on a thumbnail, and then multiply the metaphor until language strains. That is the interior of a neutron star. The rulebook says there is a ceiling to this balance. Add too much mass, and gravity ceases to bargain. The star must surrender its light and become a black hole. Yet something hidden was waiting in the dark, a way for the star to hold the line. The puzzle arrived as a series of careful measurements. Timing delays, subtle distortions, faint X-ray flickers licking the edges of a pulse profile. Each piece suggested the same audacious conclusion. The star was heavy enough to flirt with collapse, heavy enough to inhabit the narrow strip of reality where theory expects the floorboards to give way. And still it spun, steady as a skater pulling arms tight to hold a faster turn, steady as a turbine riding its own momentum. If mass is the hand that pushes the door to oblivion, rotation is the foot wedged at the threshold. The door has not closed, yet. Why should one precarious survivor matter to the rest of the cosmos? Because its very existence sharpens the blade that cuts between two kingdoms. The realm of neutron stars, where dense matter provides pressure against gravity, and the realm of black holes, where gravity writes a geometry that traps even light. If this object is as massive as the numbers imply, then the physics of dense matter must be stiffer than some models allow, or rotation must shoulder more of the burden than usually assumed, or both. In a single stubborn heartbeat, the star erases entire families of theoretical possibilities and tightens the noose on the true equation of state, the relationship between pressure and density. Inside, matter pushed past nuclear scales. Think of the equation of state as the personality of ultra-dense matter. Soft personalities give way easily. Stiff personalities push back hard. For years, the community has wrestled with whether the core of a neutron star remains an ocean of neutrons with a few exotic drifters, or whether stranger phases appear, hyperons, meson condensates, or even deconfined quarks flowing like a new fluid of liberated constituents. Each option changes how much weight a star can bear before gravity takes command. The heavier this survivor proves to be, the more it rewrites that menu. It is like finding a stone bridge where maps showed only a rope. Suddenly, caravans that were impossible become merely difficult. You can hear the stakes in the way astronomers talk about the boundary. Somewhere between the lightest black holes and the heaviest neutron stars, there is a narrow pass, a mass range where nature must choose one identity or the other. Observations have found objects marching right up to that pass, like climbers arriving at the final ridge, while wind claws at their coats. The star in front of us is not merely another traveler. It is the one that sits on the ridge and refuses to descend. If it stands where theory says no footing exists, then the mountain itself is different from what the topographic lines foretold. Listen to the rhythm of its pulses. Each sweep is a clock tick, written in gravity and magnetism, a drumbeat announcing both defiance and doom. Rotation is the scaffold that holds the structure against the crush. Magnetism threads the spinning matter, shaping radiation and carving the lighthouse beam that reaches our telescopes. Deep below the crust, Interactions between neutrons and the rare visitors among them decide how rigidly the core resists. It is a truce signed under duress, renewed with every turn. Pull away even a little angular momentum, and the balance tightens. Let the magnetic torque nibble at the spin long enough, and the door that refuses to close will inch inward. What you are watching is not a cheat code against gravity. It is a temporary reprieve written into the mathematics of rotation and pressure. The star's survival is a message encoded in light travel time and bent spacetime. And that message tells us the ceiling of stability is higher than the softest visions imagined, lower than the wildest speculations, and exquisitely sensitive to the details of nature's strongest force. This is not a curiosity. It is a ruling from a court that does not grant appeals. If you have ever wondered how the universe enforces its laws, this is the lesson. With clocks, with pulses, with the stubborn syllables of a dead star speaking across light years. And if you want more moments like this, more edges of reality brought into focus, like the video, subscribe, and tell me where you are watching from. Your voice tells the algorithm to keep bringing you to the frontier. Now breathe with the star. Feel the spin that keeps it aloft, the invisible hands that both cradle and threaten it. Picture a coin twirling on a tabletop, steady while the energy lasts, wobbling as it slows, trembling at the very end of balance. Somewhere inside those pulses is the mass that should not be borne. Somewhere inside those pulses is the pressure that should not suffice. The limit is out there, not as a rumor or a diagram, but as a line in spacetime crowded with objects daring to step over it. And if there is a hard edge to stability, it waits just beyond the next heartbeat, asking what happens when the coin tilts 1 degree more.
Chalk snapped against the whiteboard as a theorist drew a sharp line and said the sky could not cross it. On screens nearby, simulations boiled with color. Compact stars squeezed until their surfaces quivered, spacetime itself flexing like a drumhead under a final strike. You can feel the room tense when a boundary is named. The Tolman Oppenheimer, Volkoff limit is not a suggestion. It is the hard promise that gravity makes to matter. Pile on mass beyond a certain point, and no pressure born of neutrons can shoulder the weight. The star must bow. The geometry tightens. Light searches for an exit and finds only closed doors. Imagine stacking bricks on a wooden table. At first the wood bears the load with stoic silence. Add more, and the grain begins to whisper. Add still more, and the surface bows, fibers straining like 1,000 tiny ropes. The TOV limit is the moment when the ropes are no longer ropes, when the table is not a table, when the grammar of resistance fails. For a non-rotating neutron star described by conventional physics, that moment arrives somewhere between about 2 and about 3 times the mass of the Sun, depending on how stiff or soft the inner matter proves to be. Stiffness is everything. It is the difference between a bridge of iron and a bridge of reed. But how stiff is the universe willing to be? Observations have already caught pulsars that weigh around 2 solar masses, spinning with clockwork poise, their heartbeat light curves firm as drumbeats in a marching band. Those survivors are not mere curiosities. They are judges that dismiss entire families of soft equations of state. If the inner matter were too easy to compress, those stars would not exist. They would have been erased by their own gravity, their light replaced by silence. Each confirmed heavyweight clears fog from the map and draws the cliff edge with darker ink. Now look at the numbers that make astronomers sit straighter in their chairs. Instruments have whispered about compact objects near 2.5 to nearly 3 solar masses, perched in the narrow gulf between confidence and doubt. Some live in binaries where timing delays can be translated into mass with exquisite care when the geometry is kind. Others are inferred from how a companion's light is sculpted by heat and wind from the pulsar's radiation. A delicate dance where every assumption about atmospheres and viewing angle matters. Each method has its traps, each has its corrections. Yet they are converging on a frontier that feels less like rumor and more like stone. This is the gap that haunts the field. The narrow band between the heaviest plausible neutron stars and the lightest undisputed black holes. For years, that band looked empty, as if nature avoided it out of principle. Then came hints, then candidates, then a handful of stubborn cases that fall into the silence and refuse to be labeled. A compact object around 2.5 solar masses in a coalescing binary. A pulsar that might be heavier than earlier generations dared to draw on seminar slides. If those masses are real, we are staring at the knife edge where support physics passes the baton to geometry. You might ask what pressure fights in that last stand. It is not the thermal push of heat. These stars are cold by astrophysical standards. It is not the gas pressure that holds up ordinary stars. Atoms have already been crushed into near uniformity. The fighters here are quantum and nuclear in nature. The degeneracy pressure of neutrons, the short-range repulsion of nuclear forces, the possible emergence of more exotic constituents that can either stiffen the response or softening it into surrender. Add a whisper of deconfined quark matter and the script changes, sometimes to the star's detriment. Introduce hyperons, and you can steal strength from the core unless other interactions push back harder. The interior is not a single substance so much as a parliament under duress, with rules set by nature's strictest force. The ceiling the theorist drew is not a single number carved in granite. It is a band, a span, a ledge whose height depends on the character of the matter inside. For a non-spinning star with no extra tricks, the upper bound should fall in that range between about 2 and about 3 suns. Softer microphysics pulls the ceiling down. Stiffer microphysics shoves it up. Observations of radii by X-ray pulse profile modeling now hint at moderate stiffness, a delicate middle ground where the star is neither a fragile reed nor an unbending anvil. That middle ground narrows the possibilities until the chalk line begins to look like a wire stretched tight. You can hear the edge in the data from mergers as well. When 2 neutron stars spiral together, they sometimes form a single swollen remnant that glows for a heartbeat of cosmic time before collapsing. The delay between union and silence ties directly to how high the non-rotating ceiling sits. Too low a ceiling, and the remnant cannot breathe even with rotational help. A higher ceiling and the creature lives longer, hurling heavy elements into space and stamping its brief life into a kilonova. The timing of that fall is a seismograph for the hidden stiffness of matter beyond nuclear density. Hold that image in your head, a limit not drawn by preference but by equations, a ledge cut into spacetime where stars either stand or slip. The object on our screens lives near that ledge, close enough that any additional burden ought to tilt it beyond rescue. Yet the pulses persist. The signal is steady, as if a coin were spinning so fast its wobble cannot be seen, as if a tightrope walker were finding purchase on a wire thinner than breath. The line on the board remains where it is. The data presses against it like rising floodwater, and every new measurement asks a harder question. What if the chalk snaps again? Not from clumsy hands, but because the universe keeps pushing until the drawing must be redrawn in a new place. What if the ceiling is real yet higher than the soft voices claimed? Not by whim, but by the deep personality of dense matter that we have only begun to read. The monitors keep ticking, the models keep grinding, and somewhere inside the star the argument between gravity and pressure continues without pause, waiting for the smallest change that might tip a balance no one can yet see. The waveforms sharpen like a blade. Each pulse arrived with the punctuality of a metronome, a lighthouse sweeping a storm where gravity is the sea and spacetime is the wind. You can hear a second rhythm under the obvious one if you listen closely. Not just light flashing, but angular momentum talking. Rotation is not decoration here. It is scaffolding. It is the invisible truss that lets the structure hold a weight that static matter cannot bear. Take that spin away and the edifice feels the full crush. Keep it, and the star buys time. Picture a skater who pulls their arms in and carves a circle so tight the air seems to hum. That posture is uniform rotation, every layer turning in lockstep, centrifugal support pushing out against the inward drag. In that stance, the ceiling rises by a healthy fraction, on the order of 15 to 20% compared with the still case. The math translates into mercy. The star can carry extra mass without yielding, because rotation dilutes the effective gravity felt by each fluid element. The pressure does not work alone. The spin adds a stabilizing hand on the shoulder. But there is a more dangerous, more extravagant dance step, and nature performs it in the first moments after violence. When 2 neutron stars merge, their newborn remnant can whirl with differential rotation. Inner zones racing ahead of outer layers like lanes on a track. That pattern buys even more support, a hypermassive state where the mass can climb well beyond the quiet ceiling. The price is paid in time. Shear and magnetic turbulence gnaw at the differentially rotating flow, redistributing angular momentum, winding up magnetic fields, radiating energy. The remnant can live in this overclocked mode for only a brief breath, from a few seconds to a few minutes, before the extra help is erased and the core faces its real strength. Some remnants settle into a less frantic, but still precarious category: supermassive stars. These are bodies that are stable only so long as they keep a rapid, nearly uniform spin. Imagine a cathedral with flying buttresses made of motion. As long as the whirlwind holds, the arches stand. But magnetic braking is patient. It threads the star with field lines, turns the whole body into a cosmic dynamo, and bleeds rotational energy into electromagnetic winds. Gravitational waves can join the theft if the star's shape is even slightly out of round, sending ripples through spacetime like a tuning fork that refuses to quiet. Every heartbeat pays a tax, and the balance sheet trends one way. You can watch this bargain in the fastest pulsars, millisecond engines that flicker with periods of about a few thousandths of a second. Some have spins near about 1.5 milliseconds, a staggering tempo that makes a hummingbird look sluggish. These are not youthful fireworks dropping brightness in a night. These are ancient turbines kept alive by careful physics, sometimes fed by a companion star that dribbles matter and angular momentum onto them over ages, a process benign in appearance and ruthless in consequence. The feeding polishes the pulsar down to a perfectly symmetric spinner, erasing bumps that would radiate gravitational waves and pushing the mass toward the cliff. The observational fingerprints of this struggle are written in several languages. Radio timing lays out the rotation with painful precision. X-ray pulse profiles carry the imprint of hotspots dragged around by the magnetic geometry, distorted by light bending so strong that the star can see more than half of its own surface at once. Subtle irregularities called glitches and timing noise reveal the crust and the superfluid core speaking to each other, trading angular momentum like two gears that do not always mesh cleanly. Each effect belongs to a different layer of the machine, yet together they sketch a single portrait, a body that lives by spin. Now hold the thought that rotation is not merely a stabilizer, it is also a countdown. Angular momentum is a bank account with withdrawals baked into the laws. Magnetic dipole radiation carries energy away as a wind of charged particles and electromagnetic fields. If the star carries even a slight frozen mountain, a mass distortion not much higher than a human building over a nuclear-dense landscape, spacetime waves will siphon energy at a rate set by that tiny imperfection. Internal oscillations called R modes can grow and saturate, stirring the fluid and extracting spin. Every mechanism is a nibble. Nibbles add up. There is a cruel symmetry to the fate of a supermassive star. The very processes that made it possible, the accretion that spun it up, the magnetic ordering that shapes its pulses, the viscous and turbulent couplings that settle it into uniform rotation, also conspire to erode the support it needs to survive. The door to collapse stays open by a hair, and the hair thins with time. No chart on the wall tells you the exact hour when the last helpful turn slips away. The moment is written into a curve that drops slowly, then a little faster, then faster still, like a coin that begins with proud, upright spins and ends in a widening, breathless wobble. If you want to feel the stakes in your bones, imagine standing on a planet orbiting such a star. You would not survive the radiation, but pretend instrumentation makes it possible. You would hear a wind that is not a wind, taste a storm of charged particles that never tires, and watch auroras so violent they look like glass shattering in slow motion. Then one day the rhythm would change. The spacing between the pulses would drift by a fraction of a whisper. The torque balance would twitch as if jolted by an unseen hand. Something deep would have tilted. You would not know if it were the crust creeping, the magnetic field unwinding, or a mode inside the superfluid singing a louder note. You would only know the scaffold had lost another sliver of strength. Astronomers try to catch those instants with timing campaigns that span years and with instruments tuned to the faintest swell in the high-frequency sky, hoping for a murmur of continuous gravitational waves from a lopsided spinner. They map spin-down rates, fit breaking indices, hunt for correlations with X-ray luminosity and gamma-ray flares. Each trend a breadcrumb along a path that leads toward a threshold no one has seen from the inside. The story they are writing is not just about a star evading a rule. It is about a star paying for its defiance with a currency that cannot be minted again. And as the pulses continue, they carry a quiet message. The mass is real, the support is rotational, the account is dwindling. Any change in torque, any alteration in field geometry, any tiny shift in the superfluid's grip could move the needle. One heartbeat to the next, the balance could slide from barely safe to not quite enough, leaving only the aftertaste of a vanished signal and a question that no observer can ask back. An analyst dimmed the lights and let the sky speak in curves. On one screen, the heartbeat of a heavy pulsar. Each tick a promise that matter can still breathe under a mountain of gravity. On another, an X-ray pulse profile swung like a lantern over storm water, its shape warped by light bending so fierce that the star's own horizonless surface stared back at itself. You feel it in your chest when numbers stop being abstractions and start behaving like verdicts. The cases on the wall were not rumors. They were witnesses. Begin with the heavyweight whose radius was taken by an orbiting timing instrument designed to read hotspots as if they were clock hands painted in fire. The star sat in a tight binary and weighed in around 2 suns, give or take the honest uncertainty that good measurements always confess. Its radius came out near a dozen to a baker's dozen kilometers. Not a toy figure, but a narrowing of possibility that shoved soft inner physics off the table. A star that small, that heavy, and still shining tells you the core pushes back with more grit than the gentlest theories allow. The pulses are not poetry. They are pressure made visible. Now look at the predator that feeds on its companion, a black widow kind of system where the pulsar's radiation peels its partner like paint under a blowtorch. The companion's light curve rises and falls as one side is scorched and the other side cools. A slow blink that can be interpreted to weigh the devourer doing the heating. Some models place that mass near 2 and nearly 1/2 suns, brushing up against the territory where rotation must shoulder the load or gravity takes the wheel. The method is delicate. You must account for winds, for albedo, for opportunistic geometry that can trick you when the orbit tips just so. But even after the careful doubts are applied, the silhouette that remains is hulking. Across the hall, a different language spoke. Spacetime ripples recorded by an Earth-sized instrument made of lasers and patience. In the late summer of the year 2017, 2 neutron stars wound around each other like skaters clutching hands too tightly. The inspiral chirped through the detectors, then the light show began. A kilonova blossom that spilled heavy elements into the night and told us that the remnant lived only briefly before it yielded. That delay was not a shrug. It carried information. It said the non-spinning ceiling could not be too low because rotation bought a little time, and not too high because the extra help was not enough to grant long life. A boundary spoke with the voice of a dying whirl. Then came the strange visitor recorded in the year 2019, a compact object around 2 6/10 suns caught in a dance with a much heavier partner. You could call it the lightest black hole ever seen and be startled. You could call it the heaviest neutron star and be amazed. Either label rattles your cage. If it were a neutron star, it would test the scaffold of rotation to its limits. If it were a black hole, it would carve the lower edge of black hole birth into fresh stone and leave a narrow, uneasy no man's land between the two families. The event did not hand out an identity card. It left a question mark in a mass range that used to be a blank. Look again at the pulsar with a precisely measured mass that hovers just above 2 suns. In the old days, that number would have been an outlier, an awkward cousin at a family dinner. Now it feels almost ordinary, and that ordinary feeling is the revelation. It means nature does not flinch when asked to build neutron stars at the upper range of what non-rotating theory can support. It means the inner matter does not collapse at the first sign of extra weight. It means the stiffness at high density is real enough to stand in the data, not just in chalk on a board. There is also the quiet testimony from radius measurements taken by the same X-ray mapper on another massive pulsar, a sibling to the first. The inferred radius again favored a middle course. neither a marshmallow interior that would fold early nor an ironclad one that would give too much leeway. This middle course is not dull. It is razor work. It trims families of equations that cannot accommodate heavy masses and modest radii at the same time. It trims stories that add exotic particles too eagerly, without also adding the repulsive interactions that would stiffen the mix. It leaves you with a short list of viable interiors, each with a personality that must be consistent with every heartbeat recorded. When theorists fit these cases together, the pattern that emerges is not a neat graph but a coastline. Here is a promontory where heavy pulsars demand sturdier cores. There is an inlet where merger remnants collapse after a breath, hinting at an upper mass not much above the non-spinning ceiling once rotation is stripped away. Offshore lies the deep water, where a compact object of about 2 6/10 suns refuses to confess its lineage. The tide etches every detail. Each new measurement is a wave that either smooths a corner or chisels fresh rock. You can feel the tension in the methods themselves. Shapiro delay in a nearly edge-on binary gives a mass that is as honest as gravity can provide, but it asks the cosmos for a gift of geometry. Pulse profile modeling extracts radius and mass by tracing beams around a curved surface, but it asks you to trust your map of hotspots and atmospheres. Companion heating models weigh the sculptor by reading the sculpture, but they demand rigor in how you model the winds and paint the albedo. Gravitational wave events translate chirps into component masses with priors that must be chosen with care, while the glow of kilonovae interprets nuclear wreckage with opacities that are still being tamed. No single method can be king. The crown is minted only when they agree. Even with that caution, the chorus points one way. Neutron stars do not retreat from the frontier. They walk to the edge drawn by theory and place a boot across it. A few may stand on the wire with spin as their harness. A few blur their identity inside mergers where the last heartbeat and the first silence are separated by only a handful of moments. The line between star and hole, once sketched as a wide band of uncertainty, is tightening, not into a razor-thin border, but into a pass you can point at on a map and debate which side a traveler is on. The room brightens as the analyst raises the lights. On every screen, the evidence refuses to be quiet. Heavy pulsars that keep time like sovereigns. Merger fireworks that die with a suggestive pause. A mass in the uncomfortable middle that will not pick a name. If you are listening, you can hear the question beneath the data. How exactly does the interior of dense matter manage these feats? And how long can any one star balance where maps warn that footing fails? The star's skin crackles with magnetized frost while its heart argues with gravity in a language older than light. You want to know what stands between collapse and survival? Go inward. Peel back the crust, a lattice of iron and neutron-rich nuclei crushed into a grid so tight it rings like stone. Slip beneath into the inner crust where a quantum forest grows. Nuclear trees stretched and fused into rods and slabs, the so-called pasta phases. Matter sculpted by competition between nuclear attraction and electric repulsion. It looks nothing like the neat spheres drawn in textbooks. It looks like a city designed by pressure and trimmed by sheer necessity. Dive deeper, and the scenery changes from architecture to ocean. Neutrons unbind and flow as a superfluid, a frictionless river that threads the core. Protons, the few that remain, pair and glide as a superconductor, freezing magnetic flux into taut, quantized ropes. The two fluids interlock in a restless weave, vortices for the superfluid, flux tubes for the superconductor, tethered, pinning and unpinning, trading angular momentum with the stubbornness of gears that refuse to let go. When the star glitches and its spin twitches forward, that is the river slipping its pins and surging past the crust, a reminder that even perfection strains under load. Keep falling, and the pressure crosses a threshold where words like ordinary lose meaning. Neutrons, once the majority, pack so hard their identities blur at the edges. The equation of state, the rulebook that turns density into pressure, decides everything here. If the rulebook is soft, the core yields like wet clay and the ceiling for mass drops. If the rulebook is stiff, short-range nuclear repulsion rises like a hidden wall, and the core pushes back as if made of tempered steel. Stiffness buys room to breathe. Stiffness buys time. But stiffness is not a slogan. It is a balance of forces at lengths smaller than a proton. The same strong interaction that binds quarks inside neutrons also sets a repulsive shoulder when particles are crushed together. That shoulder is the brace against gravity's knee. Subtle adjustments, three-body forces, density-dependent couplings, the way neutrons and protons exchange virtual mesons. Shift the brace by just enough to decide whether a star can carry an extra fraction of the sun on its back. You can think of it like a crowd in a packed stadium. If each person leans outward even slightly, the whole stands hold. If they all exhale at once, the structure groans. Now the plot complicates. As density climbs, new actors may enter the stage. Hyperons, baryons laced with strange quarks, can appear when it is cheaper to invite strangeness than to cram more identical neutrons into the same quantum seats. That move eases the crowding but often weakens the collective push, softening the equation of state and lowering the maximum mass. Unless, that is, repulsive hyperon interactions kick in strongly at high density, or other many-body effects stiffen the brew. The menu grows stranger still with the possibility of deconfined quark matter, a phase where quarks roam more freely than in individual nucleons. Some versions of that phase are soft and treacherous, a trapdoor under the star. Others are stiffer, with strong interactions giving the quark soup a backbone robust enough to carry weight. Nature's choice here is not an ivory tower curiosity. It is a verdict with consequences measured in stellar lifetimes. Thread through this core, and you will encounter magnetic fields that would peel the paint off earthly words. Magnetars were fields 1,000 trillion times stronger than a laboratory magnet. Fields that twist crusts and power flares like tornadoes made of light. Yet even these monstrous fields offer only modest global support against gravity. They reshape local stiffness, they fracture the crust, they channel heat and stress, but their pressure is a small fraction of what is needed to lift the ceiling by more than a sliver. Magnetism is the sculptor of surface drama and the custodian of rotational torque. It is not the lone architect of survival. Consider heat. Newborn remnants after a merger or a catastrophic quake can be hot enough that thermal pressure adds its voice to the chorus, briefly inflating the balance like air under a drumskin. But neutron stars are excellent radiators. Neutrinos sprint from their cores with almost no resistance, carrying energy away with ruthless efficiency. In mere moments by cosmic standards, years then thousands of years, the thermal contribution fades, the drumskin cools, and the equation of state returns to the cold regime where quantum degeneracy and nuclear forces hold the conversation. Thermal help is a match struck in a storm, bright, important, extinguished. So where does the long-term margin come from? From the spin we already met, married to microphysics that is just stiff enough to keep pace. Rapid uniform rotation flings a little gravity outward and raises the maximum mass by a substantial fraction. That fraction is the difference between a star that dies in silence and a star that sings on. Supermassive configurations are the proof. Objects that would collapse if they stood still, yet stand because they whirl. The interior, in turn, dictates how much spin is required to hold a given mass and how fast the star's braking will steal that support. A stiffer core means the scaffold can be lighter. A softer one demands a faster turn and shortens the lease. The evidence for that interior stiffness does not arrive as a single banner unfurled from a single tower. It arrives through a triangulation. Mass measurements of heavy pulsars forbid the most delicate, easily crushed cores. Radius inferences favor a middle ground, ruling out the extremes that would give either a bloated star or a shrunken one at a given mass. Merger remnants collapsing after a breath argue that the non-rotating ceiling is not sky-high, while the existence of survivors near that ceiling means it is not floor-low either. Every line tightens the knot. Inside this knot, the superfluid and the superconductor continue their clandestine trades. Vortex lattices drift, pin, and unpin, microscopic tempests that decide macroscopic timing. Flux tubes creep through the proton sea, dragging magnetic geometry and rewriting how torque couples to the crust. If an R mode awakens, it will sing in the star's frame and pour angular momentum into spacetime waves, a siphon that can cut down the spin until the instability starves. These are not decorative details. They are the gears and governors that set how fast the scaffold thins. You can stand, imaginatively, at a boundary inside the core where the character of matter changes. where nucleons blur into something stranger, or where hyperons begin to populate the benches with their quiet, heavy presence. On one side, the star buys more time with a sturdier push. On the other, it loses time to a softening chorus. The pulses reaching us do not tell you which corridor the core has chosen. Not yet. They tell you the choice is tight, the room is small, and the margin is a handful of heartbeats spread across ages. The star holds for now. Not by miracle, by rules, by repulsion at femtometer scales, by quantum seas that do not like to be crowded, by rotation that takes some of gravity's grip and slides it along a curve. But a single adjustment, a slightly stronger hyperon coupling, a whisper of deconfined quark matter with a softer spine, a shift in the superfluid's pinning, could lean the balance. And if that lean deepens by even the smallest fraction, the scaffold that kept the geometry from closing will feel a weight it can no longer offset, leaving only the question of when the next pulse will fail to arrive. Night after night, the array kept time with a dead star's heartbeat, not as poetry but as measurement. You can almost hear the clockwork of general relativity in the background, a quiet ticking that turns light into ruler and delay into weight. When a pulsar's signal threads behind its companion, the radio pulse passes through deeper gravity and arrives late by the width of a breath. That pause is the Shapiro delay, a fingerprint of curvature etched onto a millisecond. Give the orbit a helpful tilt, almost edge-on, and spacetime itself becomes a set of bathroom scales. Each late arrival is a gram on the dial. Stack enough delays across many orbits, and mass appears not as a guess, but as the only number that makes geometry and time agree. But the cosmos is not always generous with angles. Many orbits lean shyly away from the ideal alignment, and then precision turns into inference. Pulsar timing recovers a mass function, a relationship between the heft of the two bodies and the tilt of their dance. To extract a true mass, you must know how the system is inclined, and inclination is a trickster. A few degrees one way and you crown a heavyweight. A few degrees the other way and you demote a monarch to common stock. Astronomers chase those degrees with everything they have: optical spectroscopy of a companion's wobble, subtle changes in pulse arrival times caused by the motion of the binary across the sky, even the slow dance between proper motion and orbital geometry that adds a faint, secular drift to the timing model. Each is a thread. Woven together, they become a harness strong enough to pull mass out of ambiguity. There is another language, carved in X-rays and bent by gravity so strong that straight lines are a rumor. Imagine two hot patches on the neutron star's surface, places where the magnetic field scours the crust and lets charged particles slam down, turning impact into light. As the star spins, those hot spots sweep in and out of view. On a normal world, you would see them wink on and off like lighthouse windows. Near a neutron star, light curves around the body. You see more than half a sphere at once. The pulse becomes a rounded, skewed waveform that encodes the radius and the mass at the same time. That is pulse profile modeling, using light bending to coax geometry from flicker. It asks for a careful map of the magnetic geometry and the beaming pattern of the X-ray atmosphere, which depends on composition, temperature, and gravity. It asks you to trust your instrument's calibration down to the last photon. But when the fit lands, it lands like a footstep in wet cement. Some systems give you a companion bright enough to study in reflected fire. In the Black Widow and Redback families, the pulsar's radiation bakes one hemisphere of its partner until it glows like a coal. Watch that glow over an orbit and you get a living map. Day-side and night-side trading places, winds roaring from hot to cold, star spots confounding the pattern like scars on skin. Model that map with care. Include the heat redistribution, the changing albedo, the viewing angle, the faint spill of accretion if it has not fully shut off, and the mass of the sculptor emerges from the sculpture. The method is powerful and perilous. A wrong assumption about how heat is moved or how the atmosphere scatters light can exhale a false giant or inhale a real one. Teams fight over these subtleties not out of vanity, but because a single percent in the companion's brightness can swing the verdict between ordinary and astonishing. Gravitational waves speak in yet another dialect, one that does not care about light at all. Two compact objects orbiting each other pull energy out of spacetime and broadcast it as a rising chirp. The frequency sweep tells you the combined mass and a weighted combination called the chirp mass with exquisite precision. Split those into individual masses and you must lean on the details. The tidal deformability that tells you how squishy each star is, the modulation of the waveform by spin. The prior beliefs you feed the analysis about which spins and tilts are likely. If the signal is loud and the detectors are kind, you can read those parameters with crisp clarity. If the signal is shy, you must accept that nature will hand you a range and dare you to learn within it. Then the light from the aftermath, the kilonovae, adds clues about how long the remnant lived, which ties back to the ceiling that non-rotating stars can bear. Every step is probabilistic, yet the map tightens as events pile up. Across all these methods runs a single demand. Systematics must be hunted, trapped, and named. In radio timing, unmodeled dispersion changes along the line of sight can masquerade as slow drifts. So observers split the band and measure how the interstellar medium tugs differently on low and high frequencies. Tiny clock errors in the observatory chain can spill into pulse phases, so timing networks cross-check with independent standards and redundant backends. In X-ray modeling, instrument gain drifts and background events can bias a radius, so calibration campaigns point at standard candles in the sky and compare independent detectors. In optical light curve fitting, flares and star spots can ruin a night. Teams watch over many orbits, then weight down the misbehaving epochs. In gravitational wave inference, waveform families carry assumptions about tides and spin alignment. Analysts run the data through multiple models and ask whether the answer moves in step or slips under pressure. When the results survive those trials, astronomers press them against each other like forensic prints. A heavy mass from Shapiro delay that agrees with an X-ray radius that rules out a soft interior begins to feel less like a coincidence and more like a consistency relation written in the sky. A merger remnant that collapses quickly after coalescence and a population of massive pulsars that remain stable in isolation triangulate a narrow band for the true ceiling. A Black Widow estimate that pushes into supermassive territory draws immediate scrutiny. Reobserve the companion, update the atmosphere model, revisit the system geometry, then check whether the pulsar's timing agrees with the inferred spin-down power needed to heat that much. The point is not to fall in love with any one method. The point is to make them argue until they converge. You, watching this, might wonder how close the field believes it is to being sure. The true answer is a mood and a method. Confidence comes from redundancy, from the way different instruments and distinct physical effects point toward the same strip of parameter space. Skepticism remains by design, a wall against self-deception. Teams publish with honest uncertainties, with corner plots that show the droplet of probability where mass and radius live. They return to the same sources year after year, because long baselines smooth out the wrinkles of noise and catch the rare flares that would have bent a result. They build new detectors with wider bands and quieter systems, because a single extra bit of information, a better handle on inclination, a cleaner measure of pulse beaming, a louder tidal signature, can turn a puzzle piece enough to lock it into the board. In quiet moments, someone will sketch the silhouette of the impossible star on a napkin. A small circle labeled with a mass that ought to be deadly, a note about a period that spins so fast the pen stutters, a reminder to check whether the breaking index has shifted. It looks simple in ink and impossibly complicated in reality. Somewhere behind all the models is a body that only obeys. It emits, it spins down, it couples its crust to its superfluid, it lets its magnetosphere crackle and howl, and it refuses to tell you which hidden stiffness is saving it. The only way forward is to listen longer and through more windows. The array keeps listening. The X-ray mapper keeps watching. The optical telescopes keep catching the heated faces of ablated companions as they turn. The interferometers keep their long arms ready for another chirp that could tilt the balance. Every new heartbeat adds a grain of weight to one side of the scale. And it will take only a small shift, an angle measured more cleanly, a waveform modeled more faithfully, a pulse profile with a quieter background, for a verdict to sharpen enough that the star's precarious survival can be timed like a fuse whose length no one has yet measured. The pulse train faltered by less than a heartbeat, a pause so slight that only a patient astronomer would notice, the kind of tremor that makes a room fall quiet. Spin is the scaffold, and scaffolds creak before they fail. You can feel that knowledge crawl along your skin when a millisecond stretches by a fraction more than habit allows. The star has been paying a tax on motion since its birth. Magnetic torque has been shaving energy from every rotation, peeling it away in a wind of charged particles and twisted fields. If the body carries even a whisper of asymmetry, spacetime itself carries off an invisible tithe as gravitational waves, ripples that leave the star a touch poorer each turn. A supermassive neutron star survives by these expenses staying small. They seldom stay small forever. Picture the interior like a cathedral of superfluid stone. Vortex lines spiral through the neutron river, pinned in places, loose in others, and when they unpin in avalanches, they hand angular momentum to the crust with a jolt. The crust answers with a microscopic quake, the magnetosphere flares, and the timing model grows a new scar. None of that is random mood. It is the star searching for a new equilibrium as its support thins. Slow down the rotation, and the centrifugal crutch shortens by a breath. Shorten it enough, and the hydrostatic ledger no longer balances. The central density climbs. A phase boundary advances. Somewhere in the core, matter becomes just a shade more compressible than it was the day before. There are ways a life like this can end, and all of them speak in bright syllables. One path is quiet until it is not. The pulses march, the spin ebbs, then a final threshold is crossed and the geometry closes. What follows is a silence so sudden that every radio dish on Earth hums with the absence. Yet silence may not be the only signature. When the magnetosphere is cut loose from its anchor and the field lines snap like drawn wires, an electromagnetic scream can escape even as the surface vanishes. A flash in radio, maybe a brief storm in higher energies, the dying flicker of a lighthouse as the cliff face crumbles beneath it. Some astronomers whisper about fast radio bursts as the sparks of such endings. None of them can claim the case is closed. The timing, the energetics, the environments, too many pieces still slide on the table. There is another path that takes place in the tumult after collision. Two neutron stars merge, and the remnant spins like a mad top, supported by differential rotation and heat. For a handful of heartbeats, that support holds. Then magnetic turbulence evens the rotation, neutrinos drain the heat, and the object slumps under its own truth. The slump is not sterile. Disks fling out neutron-rich matter that blooms into a kilonova, its colors shaped by the alchemy of rapid neutron capture. Gold and platinum condense in that expanding ash, dust for worlds not yet imagined. Whether the remnant survives long enough to feed a bright blue component or collapses swiftly into a dimmer red depends on the same ceiling that the isolated heavyweight tests with every turn. One fate writes more heavy elements into the galaxy. Another writes fewer. The periodic table carries a tally of stellar arguments that began before Earth had oceans. Even in quiet isolation, the destiny of a massive spinner echoes outward. The true cap on non-rotating mass regulates how often a newly formed neutron star is allowed to live, and how often it is denied that name and sent straight into shadow. Shift that cap upward and you grant more survivors. Change the demographics of millisecond pulsars. Adjust the population of magnetars that seed their galaxies with flares. Shift it downward and you thicken the ranks of low-mass black holes, carving the lower edge of the black hole mass spectrum a hair lower and tightening the contested band where nature hesitates. Birth rates are not lines on a spreadsheet. They are the metronomes of whole astrophysical neighborhoods, setting how many winds blow, how many disks shine, how many mergers the universe can stage. What we weigh in one star flows into cosmology as well. The rate and character of kilonovae stitch into the history of heavy element enrichment, a story that leaks into the atmospheres of long-lived stars and the chemistry of planets with restless minds. The stiffness of dense matter links to the tidal deformabilities that sculpt gravitational-wave signals, and those signals become rulers for distances when light and gravity arrive together from a merger. Distances become anchors for the cosmic expansion, another clock that tells us how fast the fabric of space stretches. A fraction in the pressure of neutron-rich matter can nudge a step in the ladder that measures the size of everything. None of this lessens the intimacy of the star's own moment. Listen to the magnetosphere. It hisses with outflow, a gale of pairs drawn along field lines that whip and reconnect. Keep one eye on the high energies, where a gamma-ray instrument might catch a hardening spectrum, a brief change in curvature radiation as the engine shifts torque. Keep another on the radio, where a pulse shape can sprout a shoulder, a new component flickering into existence as geometry migrates by a breath. Watch the braking index, that slow, stubborn ratio that tells you how the torque scales with spin. If it drifts, something real is moving under the floorboards. If it jumps, something deep has failed to hold. There are gambits that could prolong the balance. A core that stiffens with density more sharply than we modeled could lend a hidden hand as the star grows heavier in spirit. A deconfined quark phase with strong repulsion could arrive not as a trapdoor, but as a new pillar. Vortex pinning could behave just so, letting the superfluid shoulder more of the moment for longer than naive estimates suggest. None of these are hand-waving comforts. They are testable stories, each with fingerprints in pulse timing, glitch statistics, thermal evolution, and gravitational wave whispers that future instruments may hear. Stand with me in the control room as the next observation window opens. The dishes are aimed. The X-ray mapper waits. The interferometers hum in their vacuum tunnels like sleeping animals that sense a change in weather. Out there, the star turns, its heartbeat steady enough to be a promise and erratic enough to be a warning. Every photon and every missed photon is a syllable in a sentence we do not yet understand. If a pulse fails to arrive, the absence will be an event. If a sharp radio knife slices across the band with a single, scorching cry, the event will write a question mark into the data that theories must learn to pronounce. If nothing dramatic happens today, that quiet is not comfortable. Quiet shortens the fuse by another grain of sand. You watching this are not just an audience. You are part of a measurement that spans continents and years, a witness to a balance performed on a wire stretched over the deepest well in nature. Somewhere behind that wire, equations keep their own counsel. Somewhere ahead of it, a horizon waits like a door without a handle. Between them spins a star that should not be standing, buying one more turn with the currency of its motion, leaving us to listen for the slight change that means the bargain has shifted and a different kind of night is preparing to speak.